When we learn math or physics, we often memorize formulas without asking why they work. But in differential geometry, understanding why a formula holds is what makes the subject powerful. Proofs are not just formal steps, they are the key to truly understand the geometry of space itself. In this video, you will see why proofs are essential and how they help you to build a better understanding of differential geometry. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the 5th episode in our series of understanding differential geometry. Well, it is a very important subject, and let us first understand what is proof in mathematics. Well, most of the time what we have seen is that you have memorized formulas in physics without even knowing that why it has been done so. You have memorized and later you have forgot when it came from, or did not really know what is the practical application and how to use it in a kind of a new and challenging situation. Consider this one. The circle and its area is pi r squared. Now, do we really know what is the area and why the area is pi r squared? Well, maybe most of you know, but where does it come from? We all memorize it, but we never try to understand or find out the proof which led to a equals to pi r squared. So what we do mostly is that a equal to pi r squared is remembered as a formula. We just mug this up and we try to find out and use this in certain situations. But this can actually be deduced. This is a kind of a proof, and this is the idea of a geometric derivation to find out how the formula a equals to pi r squared came from. So I am not going ahead and deducing the proof, but this is what I'm trying to make you understand. The proof is very central not only in differential geometry but in various other areas of mathematics. So what is proof? Let us understand. We can say formally it is a kind of a logical arguments. There are certain steps. They show why a mathematical statement is true. We can build it from axioms or definitions. Now, if I give you this kind of a figure and I tell you that what is the shortest path between 2 points on a curved surface, you will definitely say that it is a geodesic. But you don't have to believe my word. You don't have to say that exactly this is a straight line. Rather, you should question yourself that what shows exactly that this is true. So the definitions are curvature, distances, and geodesics. Now, this is something which I use it at an analogy. So these are certain points. And what are those points? These points are numbers. What connect those points? Certain dots connect those points. So we can say a proof is something which is connecting the missing dots. It makes sure that there are no gaps, as you can see on the right hand side illustration, and everyone follows from a logical step. So from here what we can say is that definitions or axioms that we know are the known facts. That means you know certain things. The theorem is basically the claim. That means a mystery to solve. And proof is basically the series of logical steps, deductions, whatever you do so that it comes as a conclusion without assuming anything unproven. To give you a further example, let us say that here it is raining and we say that if it is raining, the ground gets wet. Well, it is a very mundane example, but what I'm trying to tell you is that instead of saying that if it is raining, it would get wet, you need to deduce certain proof. For example, rain is falling from the sky, the water touches the ground, it makes the ground wet. So hence we can say if it is raining, the ground gets wet. So this is a kind of a very simple proof, and it shows the logical steps behind that. There are further more complicated, many other steps are involved when we come to the true mathematical proofs. So what would be the characteristics of a proof? First of all, it should be precise. For example, if it is raining, the ground gets wet. It should be very precise and simple. It should follow the logical steps. For example, water is falling from the sky, hence it touches the ground and hence it makes the ground wet. And these are based on relationships, certain definitions, axioms, certain universal truths. And these can be reproducible by anyone who follows the same steps. That means it will always be true if they follow these steps. It will be true that if it is raining, the ground gets wet. So this is why proofs are very important, not only differential geometry, real analysis, etc. And often in my years of experience in classes, I have found that people or the students do fairly well good physics and mathematics, but they really lack is to understand what is a proof and how to prove a proof-based mathematical system. The next question which comes is that we understand what is a proof, but you tell me that why do you need proofs in kind of a differential geometry? So understand that differential geometry deals with various types of subjects which are very abstract in understanding. For example, manifold, tangent spaces. We deal with curvatures, differential forms, and various other things. So these are all abstract concepts, and these need to be mathematically proven. Otherwise, all these things would be just something which is called magical structures, which you are just told to understand, but you don't really know the reason. So if I say, for example, the Gaussian curvature K of a surface is computed by a formula, which I have not said here. So you need to know that why does this formula measures intrinsic curvature. You also need to know why does it depend on how the surface sits on space. Without the formula, the theorema egregium, Gauss's theorema egregium, you don't know whether this formula always holds true. So you are just being told, hence you are following it. So requesting all the viewers who are watching the video and who are taking up mathematics in a serious manner in their career, do not believe on anything, whoever be the authority, challenge it, try to prove it, and then you find that yes, it is true. Let us take few more examples. For example, if I say that the Gaussian curvature K depends only on the first fundamental form and not in the embedding, then without proof, this is just a mere statement. But the proof, if you do mathematically, you will see it will show the steps that all intrinsic properties depends not only on the metric and its derivative, but on certain areas. For example, if I take that tangent space at a point is a vector space of dimension n for an n dimensional manifold, without proof you might wonder why do the tangent vectors follow these rules? And the proof actually shows that in addition of derivations, the addition of derivations and scalar multiplications actually satisfy the axiom of a vector space. So the next question comes from here is this one, that why at all do we need proofs in differential geometry? I understand that these things you should not take it as somebody has told, but why do you need proofs in differential geometry? So the first thing is that to know why these formula work. Any kind of a formula, even a squared plus b squared, or whatever the formula dealing in, you need to know them. So in differential geometry, you understand is these are abstract objects, so it looks abstract. So don't take it as a rule or magic to memorize. Go through that and understand the formula of curvature, geodesic equation, and exterior derivative rules. Second is also these proofs, the more practice you do, it helps to understand that why these abstract concepts are so real. So differential geometry actually helps you to understand those concepts in a proof-based system. Why does the tangent space why does the tangent space from a vector space? Why is the exterior derivative of a constant is 0? So proofs of these fundamental tools from the ground up helps to give you a better understanding of the subject and builds up your logical skill. So what we can say from here is that proofs in differential geometry are not optional. They are the foundation. Without that, you won't be able to understand when and where to use it. So it makes the subject more rigorous, just like real analysis, logical and applicable, and you can apply it in any situation, not only for differential geometry, in physics, geometry, or whatsoever. Now, having said that you need proof, and what is proof? The next question that comes in our mind is that we understand. So how these proofs that we are trying to prove are actually connected to the concept. How do they actually connect? In this part, I will let you know something which is very important. For example, if I consider a very basic and fundamental concept, what is called a manifold. So we know what is a manifold. Manifold, if we look it locally, it looks like a Euclidean space, and globally it is not a Euclidean space, but it is something which is curved or twisted or whatsoever. If you have watched my earlier video on how to understand manifold, I have explained only how to understand manifold, the books, etc. So this is the concept. Now what is the proof? The proof tells that we prove that any near point there is a coordinate chart that makes it locally look Euclidean. So from here you can see that each concept that we assume that to be a concept needs to be proved mathematically. So why? Because we do not just assume this works everywhere. The proof guarantees that even weird shapes, or this kind of shape which you see on the left hand side, twisted and twirled, they are actually manifolds, and the same concept and the same proof actually takes place in all the different shapes. So first you get a concept, you understand that concept without challenging that, then mathematically you prove that, and that concept becomes more foundational. For example, if I talk of tangent space, what is the concept? The concept is that the tangent space is basically, at a point, is the collection of all the directions you can move it in a simple manner. And what is the proof? The proof is simple. We prove that tangent vectors obey vector space rules. That means the addition, the multiplication by scalars. So why? Because you don't just think of directions vaguely, but what you see is that the proof shows that they behave proper like proper vectors, allowing you to compute or do any kind of a mathematics. So the connection of proofs and concept is that each concept is taken as a concept, then you prove that. Why do you do that? Because you don't take it as a face value. Similarly, if I talk of the concept which I was just talking of, geodesic, what is the concept? We know that it is the shortest path between 2 points. And what is the connection? We prove that geodesics satisfy this. What is that? The covariant derivative of velocity along its is 0. So why do we do? Why? Because we are not willing to memorize geodesics as a formula. You really want to understand why they are natural generalization of straight lines. So from here, what we can understand, we can further get into concept like Riemannian metric, why it is so, curvature, why proves its intrinsic, integration of Stokes theorem, etc. So every time, remember that you are understanding a new concept. I'm talking of differential geometry right now. It can be extended to physics or real analysis also. You need to find out that concept, whether it is mathematically getting proved. That means something is either equal to or not equal to something. So that actually makes differential geometry a very deep and a logical subject, not just a collection of formulas. So from here we can finally summarize that concepts actually helps you to understand, for example, what is a manifold, what is a curvature, what are geodesics, and proofs show you why the concepts behave, why it is a curvature, why it is a manifold. And it ensures that you really don't memorize that, but you deeply understand, and how you can decide later how you can fit that to other areas of science. Having said that, you understand what is a proof, why do we need proof in differential geometry, how this proof and concepts, how do they really connect with each other. Now coming to the next part of the book suggestion would be this one. I would talk about few big books which will give you a very solid understanding of what is a proof-based mathematical system. And the first one is that Proof and the Art of Mathematics. This is by Joel David Hamkins. This is the cover of the book, and this is a kind of a customer review I have taken from Amazon. This is the photograph of Professor Joel David Hamkins, and more or less you have seen that there are a good number of positive reviews which the book is giving. Now the book is not very thick, it is not neither very intense or dense, but it gives you a clarity in terms of understanding how you would approach. So you can see it starts with the classical beginning, multiple proof, discrete mathematics. So remember, this is not only a proof for differential geometry. It is a general understanding how you approach and understand what is proof in mathematics. So this book would give you a very good engaging and mathematical statement. It has got a lot of illustrative examples, nice diverse topics, exercise and sample answers are also given, and it develops the knack of writing a proof writing skill, and it invokes a mathematical thinking. Overall, I can say it is a very valuable resource, neither very dense nor very thin, but it is a good step first to start understanding mathematical proofs. The next book is quite a wonderful one, and this is a very serious and an important book, The Art of Proof by Beck and Geoghegan. And the cover of the book goes something like this. These are the photographs of Professor Matthias Beck, PhD Mathematics, Temple University, the senior professor Ross Geoghegan, and he is the professor emeritus, PhD 1917, Cornell University. This is the Amazon review, and these are some of the reviews which I have taken from the book. Now, the most important part before I go and understand and tell you about the table of contents is that how these two great professors have made you understand what this book targets and how it is arranged. Now, here you can see that it is writing that you have reached the stage where details of what you already know. And then you will see it, they writes that we will take apart what you thought you knew and reassemble it in a manner so clear that you can proceed with the deeper mathematics, for example, combinatorics, geometry, topology, and so on. And here it tells about the target. The book is intended primarily for students who have studied calculus and linear algebra. And at the last line he writes there, the book is also for students who have less background but have strong mathematical interest. That means if you don't have a very strong background but you have a deep mathematical interest, the book is meant for you. Now, what is the target, what the book is trying to achieve? You can see to show students some important and interesting mathematics. Second is to show the student how to read and understand statements and proofs of theorems, to help the student discover proofs and stated theorems, to write down the newly discovered proofs correctly, and obviously to foster in the student something as close as feasible to the experience doing research in mathematics, and so on. So the first part is, this part is why it is very important, because the authors take the responsibility to make you understand about 1, 2, 3, 4. You need to know only calculus and linear algebra. Even if you don't have a strong mathematical background and have a mathematical interest, you can go. And what you have learned, now they are going to reassemble that so that you can do a much more better and a deeper understanding of mathematics. You can pause the video here and you can take a screenshot of this one. So it is around 180 pages. So it starts with integers, natural numbers, then it goes into understanding different notions of set theory. Without that, it is not possible. Then further topics, cryptography, complex number, groups and graphs, all these things are discussed in details. So from here, what I can say overall is that this is a very nice textbook. It balances perfectly between the mathematical rigor and an intuitive understanding. And the structure is well written because you understand it's a Springer book, and it provides a solid foundation for you to study further levels of mathematics and related fields. The next book, the third book, is very interesting and one of my favorite. It is called How to Read and Do Proofs by Daneil Solow. This is the cover of the book. I think you can understand who is the person who is sitting and thinking with his hand on his chin. This is the photograph of Professor Daneil Solow. This is the customer review, and I have taken a few snapshots which tells the book is really, really wonderful. I will straight away go ahead. Okay, this is another review which talks that it is well written, easy to understand, and so on. I will straight away go off and show you what are the contents of the book. Also, it is a little bit denser than the earlier book, more than 300 pages. So truths of it all. This is absolutely remarkable because the language I have personally gone through, it is wonderful. The construction method and then the induction, either or method. So everything, whatever you need to do a proof. Again, it is not only related to differential geometry. You can use this in real analysis, complex analysis, anything. This is an amazing book to deal with. The most important portion of this book is that here you see he writes that after finishing my graduate degree, I began to wonder why learning theoretical mathematics has been so difficult. And he writes that as I progressed through my graduate work, I realized that mathematics possessed many of the aspects of a game. And here he describes it. This book describes some of the rules of the game of theoretical mathematics. It has been my experience that virtually anyone who is motivated and who has a knowledge of high school mathematics can learn these rules. So it is fairly simple. Doing so greatly reduces the time frustration involved in learning mathematics. So it is just like a play. For example, you don't know how to play chess, but yet you just know the individual pieces, how to move, and then how you go slowly and slowly deeper into understanding the rules and play the game of chess much better. So he takes the approach of making mathematics more interesting. That is so beautiful about Professor Solow. And he also faced the problem of understanding theoretical mathematics. He now wants to remove this problem and make life easy for you. So the remarkable part of the book is that it has dealt with many books, many proofs, by contradiction, contrapositive, induction, and so on. The writing style is very simple. It has got a lot of humor, philosophical quotes. You will enjoy once you go through that. There are a lot of illustrations, examples and exercises. So these exercises are designed to challenge students so that you do more exercises, the better you are. And the latest edition I have seen that contains proofs also from discrete mathematics, linear algebra, modern algebra, and so on. So if I tell overall, this book would be is well written, easy to understand, and provides the background. It would benefit thousands of students who are frustrated by mathematics. Also, it should seriously become a part, I think, of secondary education, because and nowadays the school is different. They employ a lot of critical thinking. So those already familiar with the concept, it might seem a bit detailed, but as the introduction it is unparalleled, it is wonderful. I think this type of book should be included in any kind of a secondary education, so that mathematics is not considered to be an exclusive club, and it is his text actually democratizes the topic that can confound even the most intelligent students. So mathematics should not be an exclusive club, and this text helps democratize a topic that can confound even the most intelligent students. So that's all for today's video. I give you a brief understanding of how to read proofs, what are the important things, why you should learn proof, and the books which will make your life easier. So thank you very much for watching this video. If you have liked, please do not forget to subscribe to my channel Physics for Students and click this bell icon ringing so that you get all the notification from Physics for Students. You can further follow me on my Facebook handles, where I am active and not only posting videos but something truly interesting, and you can contact me at this email ID. Physics for Students will be soon back with more and more interesting and fun-loving videos. See you soon in the next video, but till then, may the good Lord be with you.